So we would like to find and classify the critical points of the function f of xy equals x cubed minus 3xy plus y cubed. In particular, we would like to determine if the critical points that we find are local minima, local maxima, or saddle points. So let's recall the theoretical basis behind this. So first of all, AB is a critical point for f of x, y, if the gradient of f at AB is equal to 0. This is pretty much what we need to require for this point to be a local extremum for our function and be in the interior of the domain of definition. So, or at least 4 points in the interior of the domain of definition. So, of course, this condition, and this should be a vector, translates to f sub x at AB equals f sub y at AB equals 0, which of course would mean that all the directional derivatives at the point AB are equal to 0. So then we have our theorem, the second derivative test, in which we take this determinant consisting of second derivatives of actually all the second derivatives in this. And as I'm writing this, I should say that this determinant is in fact the discriminant of the second order polynomial, of the second order Taylor polynomial of our function, and in some sense determines whether the behavior, the concavity behavior that we have is the same in all directions. So it turns out that if d is less than 0, then AB is a saddle point, meaning we have no minimum or maximum. And then we have two cases if d is greater than 0. The first case is the case where f(x) at AB is greater than 0, then AB is a local minimum. And the second case is when f(x) at AB is less than 0, in which case AB is a local maximum. There are two things that we should note here. Somebody might say, okay, what happens if f(x) at AB is equal to 0 in the case that d is greater than 0? And the answer is this can never happen. If we look at this determinant, we can see that there's no way that d is greater than 0 and f(x) is equal to 0. Also, instead of f(x) at AB, we could take fyy at AB. We're really sampling a direction. And finally, notice that we have nothing to say about the case that d is equal to 0. In some books, we see that we see people say that it's a that the test is inconclusive, but it's better not to say anything. It's better to understand that this statement is useless for the case that d is equal to 0. Usually, you have to look at the second order Taylor polynomial in that case separately, or go even, the third order Taylor polynomial, or go even deeper in order to understand what happens in that case. But in most standard problems that we're going to encounter in this context, this case is not going to occur. So now with this theory in our hands, we're ready to proceed. So we start by taking the partial derivative. So we have 3x squared minus 3y, and f sub y, which is 3y. Oops, let's see. It's minus 3x plus 3y squared. Okay, just write them in the order that they occur. And we're supposed to set them equal to 0. And if we do so, we can multiply by 1/3 both equations, and they will get simplified. We will get x squared minus y equals 0, and minus x plus y squared is equal to 0. And this is really the system that we need to solve. It's a nonlinear system, and most of these systems will be impossible to solve. But if it is possible to solve it, as it will be the case with the examples that we're going to see, then a good attempt to solve such systems is to have some kind of factorization, or to try to solve for one variable and plug it into the other equation, which is what works here. So we see that y is equal to x squared from the first equation. So we take that and we plug it into the second equation, which will give us minus x plus x squared is equal to 0. And now we can work out this equation. So we can see that we get minus x plus x to the fourth is equal to 0, or x to the fourth minus x is equal to 0, same thing. And if we factor out x, we get x cubed minus 1. X cubed minus 1 has root 1. So after a synthetic division, or if we know the simple identity, here we get this, and this has no roots. This has no roots, which means that x can be either 0 or 1. Now, remember that y is equal to x squared. So if we use this, then we get that x equals 0 implies that y equals 0, and that gives us the critical point 0, 0. If x is 1, then this implies that y is 1, and we get the critical point 1, 1. So these are the two critical points we have to work with. So we're done with the find part. We found the critical points. Now we need to classify them. And for that reason, let's find the second order partial derivative. So first of all, f(x)(x), how do I find f(x)(x)? I look at fx and I differentiate once more with respect to x. That will give me 6x. Then I turn to fxy. I take again fx and I differentiate it once more with respect to y. And that gives me negative 3, which is of course fy, f sub y x. And finally fyy, which is going to be 6y. Okay, so now let's work with the point 0, 0. What is d? Again, let's take a look at what we have to place. Here is d. Okay, so that means that we will have f(x)(x) at 0, which is 0 here, 0 here. So we get to zeros on the main diagonal, and -3 and -3 here. That gives us a -9, which is less than 0. And this means that this is a saddle point. And let's see what happens with 1, 1. And d is equal to, what do we get? 6 here, 6 here, right? And then -3 and -3. So this is 36 minus 20 minus 9, which will give you a 27, which is greater than 0. And that means that we have a local extremum. Now, what kind of extremum do we have? Well, f(x)(x) at 1, 1 is equal to 6, which is greater than 0. So that means that we have a local minimum. So we have two critical points, 0, 0, which is a saddle point, and 1, 1, which is a local minimum, and that completes our classification of the critical points. Thanks for watching.